kind of doing a forensic job here, looking at a bunch of stuff that happens in the centers of some of these galaxies and trying to piece together what's the cause of it. And it's a little bit like a crime scene, actually. And so each of these different pieces of observational information, I've got to go with the observational evidence first, tells you something about the monster that produced all of these observational phenomena. This is this is an actual data picture here. See this huge fuzz? It takes up most of the picture here, and it gets brighter at the center here, Space Telescope picture, so we could get good resolution. What's all this fuzz? The starlight from the brightest elliptical galaxy in our nearby Virgo cluster of galaxies. We're sort of on the edge of the Virgo cluster. We're mildly being accelerated towards it. I guess if you wait long enough, we'll eventually fall in there many, many, many tens of billions of years in the future. The famous M87 with the spectacular Event Horizon Telescope synchrotron ring. Okay. But of course, this was not known, obviously, in the 1950s and 1960s. All it was known is there's kind of a remarkable point-like, looks stellar, quasi-stellar source of light in the center of this galaxy. Otherwise, in this case, it's an elliptical galaxy. I showed you a bunch of pictures in the lecture from last Thursday of spiral galaxies, which has a similar sort of deal. It looks like there's a star, maybe even much brighter than this, in the center of a spiral galaxy, and that's no star. That doesn't have a spectrum like a star at all, but that's about all people knew for quite some time. Actually, this one is so nearby, it was actually known from very good ground-based images. And it's very obvious if you have a radio telescope that can make high resolution images. What's the method? Radio telescope, of course, has a terrible resolution, right? Because it's just lambda over D, and lambda is huge. It's awful. Unless D is not the size of your antenna, it's the length of your baseline of your interferometer. So a radio interferometer could get you resolution as high as Hubble. And what the radio astronomers noticed in many, many cases, first of all, they unexpectedly saw all of these radio sources in the sky. And you notice a number of distinctive characteristics always associated with this radio emission. And one of them is that it often, typically, has these jets sticking out of it. It looks like this jet goes right back into the center. It looks like it originated in the center there, and it extends way out there. In fact, this thing is going, it's like leaving the galaxy, apparently. This is bluish light. It's synchrotron light. Now, in this image, it actually can be, it produces mostly radio, but it also does produce some optical, a little bit of optical light that you can see if it's nearby. Yes. So you see that this radio jet extends very, very far out. In fact, if you look further, it keeps on going out. It leaves the galaxy, and then it sort of dribbles off here, just in intergalactic space. This is enormous. So this is hundreds of thousands of light years on the picture up here. As you zoom in, you see, okay, there's a jet coming. It's pretty obviously coming from the center. As you look really closely at the center, you can see that it really seems to be coming from even just a few light years. This is the highest magnification until EHT, worldwide interferometer, came along, operating at millimeter wavelengths to get maximum resolution. You look closely, you see that this looks like a ring. It's like a circle that I showed you there. But anyway, there's a jet coming out of it. It kind of looks like it's distinctively one-sided, doesn't it? But if you look on a larger scale, and this is very common in these so-called radio galaxies. Remember, these were discovered basically as soon as people started cataloging radio sources. There's a second lobe on the opposite side, two beams blasting out of the center of the galaxy, one going left here, one going right here. Now, remember what this is. This is synchrotron emission. Synchrotron emission does require highly relativistic electrons. They have to be going at almost the speed of light with a very high gamma factor, and then they will give off these radio photons. Well, of course, normal stars don't produce that. They don't accelerate to the speed of light, electrons. It's impossible really for anybody to imagine how any combination of stars could make jets coming out of two sides of the center of a galaxy. I mean, supernovas don't do this. Even if this was an entire galaxy full of a million supernovas or something, it wouldn't really do this, would it? It became apparent that there's something that has been blasting out energy, at least in one direction or two directions. How fast? Well, it turns out you can actually measure proper motions in this jet. As you see, there are little lumps and blobs, concentrations here. These actually move out over a few years. Now, for them to go a few light years in a few years sideways, it means that they must be, these jets of energy, of highly energetic electrons, must be going at almost the speed of light. So that's a fascinating mystery, but it's been happening for hundreds of thousands or millions of years because it keeps going out in more or less the same direction here. There's some object, just one object, basically, in the center of this galaxy, which is acting like a gyroscope because it has a long-term axis that it remembers. It remembers it for hundreds of thousands of years. Looks like it's got a North Pole and a South Pole, but it's bipolar. That's a very characteristic observation of active galactic nuclei. So there's not too many explanations that you can come up with that, except, it's one very large object that remembers a North and a South polar axis. Basically, the modern interpretation is that this is a giant black hole, which probably has a disk of material spiraling around it. Black hole may be spinning or it may not be. It maintains a long-term bipolar structure or memory. The radio astronomers kept finding more of these, and nobody predicted this. It was a complete shock. This doesn't happen in most galaxies, but it happens in some remarkable radio galaxies. Just another one. This is the brightest radio source in the constellation of Cygnus, observed at high resolution. I think this is by a former UCLA student who worked on this. Here's the actual center of the galaxy, or there's an optical picture of the center of the galaxy. It happens to be a big elliptical galaxy. But if you look in the radio waves are shown in red here or orange here. This beam of high energy electrons has left the galaxy. It's gone out in intergalactic space, and then it sort of runs into some obstacles and eventually loses its thrust and sort of just makes a puff of energy here. This is a very typical double lobe radio galaxy. But you just look at this and you can sort of see where the energy originated. It should be pretty obvious to you. The energy started here and moved out in two almost exactly identical opposite directions at nearly the speed of light. And it's been doing it for hundreds of thousands or million years. But that still doesn't tell you, well, what kind of object would be able to blast high energy electrons, accelerate them out of a North and a South pole? How could that be done? As I said, no group of objects, stars, neutron stars, supernovas, or whatever, could do that because you couldn't get them all lined up. How would they all be pointing the energy to just come out in two different directions? You basically need one object with a spin axis. We already learned that it was a very small object producing the energy because it has rapid time variations in its brightness. It must correspond to an extremely high mass, because otherwise all of the radiation pressure of the photons would just explode the object. Now we've learned something else. This mass has a gyroscopic memory of the spin axis. Okay, can you tell where the quasar is in this picture? It's burning out the Hubble Space Telescope camera. It's up here in the upper left corner. You see a lot of these famous objects that are radio galaxies or quasars, quasi-stellar radio sources. You'll see 3C in front of them. Radio astronomers in the world, the leading group was in Cambridge. They had the first antennas. Actually, some of them were involved in military radar with the UK during the war, and then they took this technology and started mapping the sky after the war, and they made a catalog. The first two Cambridge catalogs were called the 1C and 2C catalog. Well, first Cambridge and second Cambridge catalog. They're basically all garbage because they couldn't pin down where the actual radio waves were coming from. It's totally unreliable. a lot of fake sources, which are called side lobes of their antennas and so on, where it's actually not even looking at the right source. It's picking up radio waves from another source that's a few degrees away. They were a disaster. Finally, after a few years, they got their first catalog that was believable, where they actually knew where the radio waves were coming from and they weren't fake sources and artifacts. Third Cambridge catalog, very influential. It only has about 500 quasars in it, but they're the brightest ones in the sky in the radio wavelengths, and so they've been studied a lot. This is bright enough to actually see with binoculars. Okay, it's like 12th magnitude, so it's too dim to see by the naked eye, but it's insanely bright, and yet it has, fairly substantial redshift. It's going away from us at about 1/6 the speed of light. So, interpreting by Hubble's law, this is crazy luminous. This is like hundreds of times more luminous than the entire light produced by the Milky Way galaxy. And yet, I've studied this object to death, we've seen this object vary in the course of one night. So all of this power and luminosity at all wavelengths, ultraviolet, X-ray wavelengths, gamma ray wavelengths, radio wavelengths, optical wavelengths, infrared wavelengths, all this energy is coming from a region that can't be more than one light day across. This one also has a jet here. UCLA graduate student Fred Baganoff finished his PhD thesis working on distant quasars with me, studying their X-ray emission. And he was looking around at postdoctoral jobs. He wanted to stay in astronomy and do research, because why would you want to do anything else? And he had this job offer to work on the Chandra data at MIT. And he says, yeah, but I really wanted to work on quasars. I didn't just want to work on the Milky Way galaxy. That's the data that they're analyzing. I said, well, you never know. Nobody's looked at the Milky Way this closely ever before. It's probably going to be fascinating data. You're certainly going to learn something about it. Why don't you give it a try? Anyway, the rest turns out to be history, because without prediction or expectation, whatever, Fred is looking at this data. It has enough magnification to just see the X-rays coming from the exact center of the Milky Way galaxy. And every once in a while, it just like explodes or just gets really bright. So usually our giant black hole is starving and doesn't have any fuel. Without fuel, it can't produce any of these energetic phenomena. It can't produce photons at any wavelengths. But every once in a while, a new blob, maybe it's a new star, a new planet or something, spirals in and gets torn apart. We actually have seen this in some detail. And then for a little while, accretion happens. So you have the possibility of gravity power. What's gravity power? Well, in a black hole, of course, it has enough gravity to accelerate mass. If there is some mass nearby, it can accelerate the mass up to the speed of light. The mass is going to acquire a huge amount of kinetic energy. If there's some way that huge kinetic energy of this mass, you need fuel, you need mass, you need a huge gravity to accelerate it. That's the first two things. If there was some way that huge kinetic energy could get transferred, I don't know, into heat, then you might see something, any hot object radiates furiously photons. You might see a really bright object if it had enough fuel. Rapidly moving stuff, gas that's moving at almost the speed of light. How could you transform that kinetic energy into heat? Any ideas of people's? Where do we get heat from usually around here? Friction. Watching the X-ray emission from the center of our galaxy for years. He's made a very successful career out of it. And you can't predict it. It's worse than the stock market. You don't know when it's going to go up. So there's an example. I think this may have been his first discovery here. Yeah, it was like doing almost nothing for 2 hours, 4 hours, 6 hours. But then during this one little 2-hour interval here, it gets to be beautifully bright. And since then, sometimes it gets to be 50 times, 100 times brighter than that. What does that immediately tell you? This whole thing was over in about 2 hours. So we immediately know that the X-ray power source in the center of our galaxy is less than 2 light hours across. That's like the inner solar system. X-ray emitting region, I guess you might call it a very low power quasar, is tiny. All right, isn't that crazy? So it looks like, yes, if you look carefully at it and you really understand the different manifestations of phenomena, looks like we've got a giant black hole in the center of our galaxy, occasionally lighting up when it gets an occasional meal. This is a computer simulation of a disk of gas around a black hole. It's orbiting around in this axis. It's gotten very, very hot. Why has it gotten very hot? I stress, although this is a computer simulation, it's extremely realistic. It's done on a supercomputer. You see the disk of gas, that if gas falls in, from a very large radius to a small radius, by the time it's gotten close to the center of gravity, close to the black hole center of mass, it seems to be spinning really fast. That should not surprise you. What's the rule, the law of physics that you might expect? That gas, if it falls down to a very small radius, is going to find itself spinning very rapidly. Conservation of angular momentum. So this gas could have fallen from nearby stars or gas clouds in the galaxy, but eventually, and it probably wasn't, it had a little bit of angular momentum, a little rotation, let's say in this axis. The spin axis would be vertical in this picture. Okay. As it gets closer and closer, conservation of angular momentum means it's going to spin faster and faster. So it can only collapse down easily perpendicular to the spin axis, and that's why you'd expect to see a disk. Didn't I go through that argument when I was talking about why galaxies make disks? Didn't I mention that argument why planetary systems, when they collapse around a star, similar deal, they usually make disks, don't they? There's disks all over the place because of conservation of angular momentum, and it's very likely, there's pretty strong evidence, there's also disks of gas around giant black holes. So far, you've got a bunch of gas, and it's just going around in orbit, and that doesn't by itself release any energy. It has to change its orbit. It has to move to a smaller radius, a tighter orbit, and go faster. What would do that? The gas in the inner parts of this disk are going fastest. In fact, the inner part is just going almost the speed of light. As you move very fast. As you move further out, gas immediately a little further away is not moving as fast. And then you go a little further away out here, and gas is moving even a little bit slower, right? Reminds you of the Keplerian rotation curve. So what you've got is an interesting situation because you have gas in a disk moving at huge velocities, but there are huge relative velocities as the inner gas is trying to move past the outer gas, and the outer gas is trying to move past gas outside of it. So you have all of these different velocities. What if they touch each other? What if there's any kind of, it's called viscosity. If there's any connection, actually it could be done with magnetic fields, if there's any connection where this inner gas has any influence on that gas that's further out, and that has any influence on the gas that's further out, and so on, there's going to be an immense amount of friction. And this does two things. Gas that's moving around at the really highest speeds, because of friction, it's going to, better write this down, lose angular momentum. Funny thing about gravity, if you lose angular momentum, what happens to that gas? Just think of, decaying orbits, spacecraft around the Earth. It's going to spiral in on a tighter and tighter orbit to smaller and smaller radii. So this is the irony of gravity. Friction is trying to make this gas slow down. But what is the result? The result is it spirals in closer and it goes even faster. Isn't that funny how gravity does that? So now we have a way for angular momentum to be transferred out. Gas can be transferred in. It can accrete. It can fall all the way in to the event horizon. So what I've described now is not just a disk of orbiting rotating gas. It's an accretion disk. because friction inside it is continually making the gas feed the black hole. This is a great way, by the way, to feed a black hole. The worst way would be to just drop rocks or planets or gas straight in, like with zero angular momentum, like that. Why is that a crummy way? To speed up to the speed of light, go inside the black hole, inside the event horizon, and we're not going to hear anything from it. We're not going to see anything. All the energy goes into the black hole. The black hole, what would happen? Not much, except that its mass increases, right? Because the black hole's mass is the summed history of all the total amount of mass that ever fell into it in its entire life history. But aside from that, we don't see anything. It's boring. The clever trick that's so nice about an accretion disk, it lets the gas gradually spiral in and get faster and faster and faster. What was the second consequence of the friction in an accretion disk? Well, friction means some of this extreme kinetic energy of orbit, some of this orbital energy, you got it, is converted into heat, which is then immediately converted into radiation. So this gas disk, the gravitational potential energy gets converted into radiative energy, and close to a black hole, oh my God, is there a lot of gravitational potential energy, the most ever. Suppose that I have a kilogram of hydrogen and I ran it through nuclear fusion reaction, so then it's going to make 0.993 kilograms of helium at the other end. I've converted basically mass into energy. So I have mc squared times what? What's the efficiency of nuclear fusion? 0.7%. Right? You could just work it out. I said you start with 1,000 grams of hydrogen, you end up when the fusion reactions take place with 993 grams of helium. That 7 grams, it's 7 out of 1,000. Those 7 parts out of 1,000, it's less than 1%. They didn't disappear. It's been transformed from mass into energy by multiplying it times c squared. And that was an incredible discovery, right? Amazing, change the 20th century there. Whoa, this is so much better than the trifling amount of energy released when you just restructure the electrons, like in a hydrocarbon. That's nothing. Like jet fuel, which I'm quite reliant on these days, by the way. Burning jet fuel with oxygen, there's almost no mass converted into energy at all. It's like nothing. Nuclear energy, whoa, that's like thousands of times more powerful, right? Instead of a kilo of jet fuel, take a kilo of hydrogen, for example, in a hydrogen bomb. That you would think is an amazing energy source. How could you beat that? That's got to be like the most efficient way of taking fuel and generating energy that the universe has ever discovered. Wrong. As of the 1970s, whatever, people realized that's not that impressive at all. Nuclear fusion only gives you about less than 1% of the fuel that's consumed gets converted into mass. In an accretion disk, under the right circumstances, like I'm describing here, actually can be 10 to 100 times more. The gravity power around the outside of a black hole is by far and away the most efficient way, if you give it fuel, to convert that fuel into energy of photons. Photons at many different wavelengths. Basically, photons corresponding to the high temperatures that you find in the inner parts of this accretion disk. So we now have pretty pieces of a good story. We have arguments why there is a giant mass in a small space, sounds like an event horizon is formed, and now we have it would have a spin axis, probably defined by whatever the random angular momentum was of the fuel that's been eating for the last millions of years. Got that. This could be the North Pole, that could be the South Pole. There are some theories basically about how magnetic fields in this that are sweeping around. It's like a gigantic dynamo when you have a sweeping magnetic field. This stuff is probably very magnetized. There are some theories about how very high energy electrons would get accelerated in 2 directions, the North and South Pole. And we have a good theory about how so much light, ultraviolet light, and so on, could get produced very close to a black hole. And that would explain why it changes its brightness rapidly over a short time, because it's all in a crazy compact region that we're seeing. Most of the light here is really coming from about 10 or 20 gravitational radii, GM over c squared. Now, we usually say that the event horizon for a hole that's not spinning is the Schwarzschild radius, which is 2 GM over c squared. I took a quasar spectrum here. Spectrum, this is how bright it is, and here are different wavelengths from the infrared to the optical to the ultraviolet to the far ultraviolet. The energy you get out is at all these different wavelengths. Why is the energy you get out at all these different wavelengths? Because you're looking at all of these different regions of the accretion disk around a giant black hole from the innermost regions, which are the hottest, small surface area, but very hot, which produce ultraviolet, extreme ultraviolet radiation, to the middle regions here. This is out to about 100 GM over c squared, which produce blue light, violet light, to the outermost regions of the disk, which produce visible light and infrared light. There's a formula for this that predicts all of this stuff. So my great achievement here was to show that I could actually match up the observations, basically of all quasars, with a simple model of an accretion disk around the black hole. I could even tell you what the rate of fuel is going on to the black hole, and in some cases, it's like more than 1 solar mass per year. In some cases, it's like a few Earth masses per second in the most luminous quasars. The other thing I could tell you is how big the black hole is, how massive it is. That basically tells you the temperature of this material. A lot of these quasars we studied, when you compare them to an accretionist model, you get the black hole mass, you see how fast they're generating luminosity, which is controlled by their fuel supply. They're not too far from the Eddington limit. Remember the Eddington limit? Well, it looks like these objects know about the Eddington limit. They really are. Some of them are on the verge of losing their stability and just blowing themselves apart. In fact, some of their outer layers may occasionally be blown away by so much radiation pressure, because all this gas is ionized. So you've got electrons, you've got electric plus and minus charges separated. As soon as they're separated, yeah, they're moving around at pretty high speeds. It's hard to avoid magnetic fields forming. In fact, that's a big argument, how strong the magnetic fields get. And so on, there might be as much energy in the magnetic field almost as there is in gas pressure. And so I'd say one of the biggest incompletenesses in this theory of accretion disk is, well, where are the magnetic fields and so on. And that is difficult to measure, but they're probably playing a pretty important role. And it's virtually certain that they cause those radio jets. It's certain that the really strong magnetic fields that are whipping around, spinning around, accelerates electrons to very high energies. But that's about all I can say that people would really agree on. An accreting black hole is fundamentally the central engine. It's what's driving all this emission. But then the radiation goes out in all directions. And then it may produce other observable consequences. We've already seen some observable consequences. It may make a jet of synchrotron emission. Maybe it may make 2 lobes of high energy particles, radiating in the radio wavelengths. We could see that with radio telescopes. Also does some other stuff. A lot of these photons are ultraviolet photons. A lot of them have a high enough energy to ionize gas. So if there's any gas around the quasar, which I suppose there would be, it's the center of a galaxy, in many cases a spiral galaxy, of course there's gas in the center of a galaxy there. That gas is going to, what happens to it when it encounters these high energy photons? Photoionized. So it's hard to imagine a quasar producing all of this UV and X-ray radiation without also producing a large amount of ionized gas. What's so special about ionized gas? Ionized gas is wonderful because I can detect it real easily if I've got a spectrum. It's totally different from what stars do. Stars have photospheres, they have absorption lines. It doesn't look like spectroscopic like stars at all. And I know the wavelengths if I measure them in a laboratory, so I can use the Doppler shift to measure accurate velocities of gas close to a black hole. An average of 700 quasar spectra. Now you can do this with thousands of quasar spectra. And we're going all the way down in the ultraviolet here. In the violet, here's the blue, here's the green, here's the yellow. This is optical wavelengths. So you see all of this quasar light, and there's no absorption lines in this. But all of these wiggles up here, they go up, are emission lines from ionized gas, and a lot of them have been identified here. And the first thing you notice is, my gosh, there are some really highly ionized atoms there. Look at this. There's carbon in its fourth ionization state. That means carbon has lost 3 electrons. Here's nitrogen 5. Nitrogen has lost 4 of its outer electrons. The outermost electron is weakest held. Why? First of all, because there's not that much net charge attracting it. You've got almost as many pluses as minuses inside. There's only an extra plus charge of 1. So it's only being held by a fairly weak electric attraction, and it's fairly far out. You know, the electric force is 1 over r squared. So it's going around out there. It wouldn't be too hard for that outer electron to be completely knocked away if it just had escape energy. Where could an electron in the outer orbit acquire escape velocity? 2 ways. One is if the atom was going really fast, I mean very fast, at a very high temperature, and hit something else, hit an electron or collided with another atom. That's going to require really high temperatures, like hundreds of thousands of degrees. There's some other way, say it's only, 10,000 degree gas. Where could that electron pick up enough energy to escape energy, to ionize? If enough energy was delivered just to that one little electron in a bundle of energy called a photon. In fact, it needs to be an ionizing photon. It needs to be a UV photon. Well, quasars are producing UV photons by the truckload above 13.6 electron volts. That's 1 Rydberg. Remember what that is? That's the ionization potential to knock away 1 electron from a hydrogen atom from its ground state. So UV photons are produced by some stars, and they barely have enough energy to knock away 1 electron. Hydrogen, you're done. It only has 1 electron. But what about some of the other heavy elements, such as we see here? Carbon, for example, magnesium, silicon, nitrogen, and so on. They have more electrons. Well, the second electron is going to be a lot harder to knock away. It's a little closer. There's more electric attraction to it, so it's going to need more energy to escape. Where are you going to get more energy? Don't tell me, oh, it'll take 2 photons. Wrong answer. The photons only come in 1 at a time. It needs 1 photon with maybe twice as much energy. What does that mean? Twice the frequency. E equals h nu. So now we need extreme ultraviolet photons to ionize, to knock off the second electron. To knock off the third electron here, we need almost X-rays to do it, or the fourth electron here, the fifth electron, we need X-rays. I'm sorry, there's no stars in the universe that produce that. They just don't get hot enough. Sorry. But the inner parts of a quasar accretion disk definitely get that hot. They produce extreme ultraviolet, very highly ionizing photons. They produce X-rays also. So you might expect to find around a quasar, because of the nature of its super high energy photons, ions that we have never seen anywhere else. Highly ionized gas, and that's what you're looking at in this spectrum here. But there's something else that's so no surprise there. And this is not what you would see when you look at the Orion Nebula, because the Orion Nebula is only being ionized by O stars, 30,000 degrees, 20,000 degrees or something, and they don't have a lot of these emission lines at all. So let's look at this emission line here. Hydrogen beta, that's a 4 to 2, n equals 4 to n equals 2 electronic transition. of hydrogen after it got ionized, and then it recombines there. It drops down the ladder, drops to the fourth level, then drops down to the second level, gives up a photon. Well, all these photons should be at what you would measure in a laboratory at rest wavelength. Your laboratory is not moving. It would be at 486 nanometers here, 4861 angstroms. But your eye is not fooling you here. There's a lot of photons here. These are H beta photons. They started at 4861, but they are significantly either over to the blue or they're over to the red. What I'm asking you to believe your eyes is some of these emission lines, in fact, most of these emission lines are wide. They're too wide a range of wavelengths. What is the one reason that I can think of why a photon might originate with a very well-known defined wavelength of 4861, but we observe it at a substantially longer, shorter wavelength? What's the one effect that is likely to be the culprit here that's doing this? Doppler shift, highly ionized gas, hydrogen, carbon, nitrogen, oxygen, moving at very high speeds. This Doppler shift here is like a few percent the speed of light because it's a few percent shift in the wavelength. So we've got gas moving around at thousands of kilometers a second, which normally would just escape any normal galaxy. Why do you think it has such a high velocity, this gas? Seems like it must be being accelerated by something very powerful. Maybe it's being accelerated by a very strong gravity that it's close to the center of. Looks like GM over R here must be, let's see, the square root of that, must be several percent the speed of light here. Meaning that this highly ionized gas is actually showing us what the conditions are relatively close to a giant black hole. Maybe they're orbiting around a giant black hole. I told you that the fuel supply and this accretion process of gas fueling the black hole to produce the ionizing energy, to produce all the UV and X-rays, is quite unstable. It's changing all the time. So the quasar is constantly changing its brightness. What's the effect of this variable amount of ionizing photons coming from the source going to be on that gas that's close to it? The gas is alternately getting a lot of power to make strong emission lines, and then the power is going down. I would expect that the emission lines of this gas, the ionization of this gas, is also going to go up and go down when the power source goes up and goes down. That's just physics. Energy in equals energy out. We have less energy, everything goes down. If we have more energy, you get more bright emission lines. Here's the fun part, though. Remember, the gas is not at the center of the AGN. It's not at the center of the quasar. It's not in the central inner solar system. It's not in the central few light hours or even light day or whatever. It's further out. It's called the broad line region. That's a stupid name because it makes lines. So it's the gas that makes lines, and the lines are broad. All these terms were named by people who didn't know what they were talking about, right? They were just describing unexplained observations. Here's the experiment. I want to watch with a lot of patience, and I'm sorry, but I'm going to have to request quite a lot of telescope time for maybe months in a row, just to look at my favorite quasar. I'm going to watch and see as the ionizing energy coming out of that quasar goes up, peaks, goes down, bottoms out. Those photons only travel at the speed of light to reach the gas that produces the broad emission lines. There maybe is an accretion disk around a black hole. It's even black at the center. That's super hot. It's producing ultraviolet and X-ray photons. And let's suppose that it wasn't producing very much at the beginning of the movie. All of a sudden, it gets an extra spurt of accretion. It produces like 10 times more power. The ultraviolet photons zoom out in all directions. Some of them are going to come straight towards the Earth. The Earth is in this direction, straight up. Some of them will go out sideways, though, also at the speed of light. That's one thing I know about photons. They travel at c. So they'll go out at the speed of light. They'll hit some of these gas clouds out here, which are moving at high velocities. They'll make them be brighter. They'll get more ionized, more emission. And then later, we'll see those emission lines get brighter. Here goes the movie. It's only 5 seconds. Watch carefully. Boom. A flash. Some come straight to the Earth. Aha. One more time. Boom. Some will go straight, the continuum goes straight to the Earth, but the emission lines come later. Here's the final frame of the movie. All right. So what are we predicting here? We will see the energy output of the quasar from the accretion disk go up first. Later, because of this lag here, this light travel time, it has to travel across to reach the ionized gas. Later, we'll see the increase in the emission lines getting stronger. And we could measure how many days it was between this and this, which corresponds to the light travel time from here to here. So if I can capture this lag or delay in actual data between emission lines and the UV continuum at central source, I can tell you how big this is. Even though until very recently, there is no telescope on Earth which can give you that much magnification. There's actual data. This is a nearby Seyfert galaxy. It's like a quasar. It has broad emission lines. It's called a Seyfert galaxy just for historical reasons because it's relatively low power and nearby. So you can actually see there's a spiral galaxy in it. Carl Seyfert, working at the Mount Wilson Observatory, actually discovered these things. Later, some more powerful examples like 3C273 I showed you there, that thing looks almost like a star. Unless you look really hard, you can barely see a faint distant little galaxy around it. Quasi-stellar object, Seyfert galaxy, they're just different amounts of power of matter accreting at different rates onto a black hole. It's pretty unpredictable. Got brighter, got fainter, got brighter, fainter, and so on. Each of these tick marks here is 10 days. We've got, I don't know, 180 days here of data. The emission lines from the ionized gas that's photoionized also responded to the brightness changes of the quasar. Quasar goes up, quasar goes down, emission line goes up, emission line goes down, and then up again. If I draw a line through the center of the peak output that we see from the quasar, that's not at the time of the peak output of the emission line. The emission line is delayed, I'm going to say, by about 10 or 15 days. Right? This is where the peak output energy was, but you have to wait 10 or 15 days for those photons to travel, 10 or 15 light days to hit the emitting gas. That gives us an actual size of this emission line gas through this indirect reverberation mapping time variability campaign. We concluded that these various different emission lines have lags of 10 days, 20 days. Some of the emission lines, like nitrogen-5, that's a highly ionized nitrogen, are coming from very close to the black hole, only a few light days out. Some of them are coming from further out, 20 days out. These are all different emission lines here that we measured. What do you want to compare that with? What is the velocities of the Doppler effect sees in these broad lines? How broad are they? How fast is the gas moving? All have the same value of v squared r, implying that they all have just one mass causing their acceleration. The location of this line, then, if you assume that all of those motions are just gravitational orbits, it tells you what the mass is doing the orbit. This is a little bit like the Andrea Ghez Galactic Center Group measurements, also at UCLA here, except she was studying individual stars. Either way, we think that this is a way to measure black hole mass.